Welcome to Local and Distributed Matrices. After completing this lesson, we should be able to understand local and distributed matrices, create dense and sparse matrices, and create different types of distributed matrices. Matrices can either be local or distributed, or dense or sparse. First, we will go through local matrices. Local matrices are the natural extension of local vectors. Similarly to vectors, matrices indices for both row and column start with a 0. Also, all values inside a matrix must be doubles. And just like vectors, local MLlibs matrices are stored on a single machine and they can either be dense or sparse. MLlib also has distributed implementation of matrices, which I will cover later in this lesson. It is worth noticing that in MLlib's implementation, matrices are always filled in column major order. Let's begin with a dense matrix. A dense matrix can be thought of as a reshaped dense vector, since it is also stored in a double array. It can be created by specifying its dimensions and an array with its values. Remember that these values will fill the matrix column-wise. This is a simple example of a dense matrix. After the appropriate imports, I create a 3x2 dense matrix by calling matrices.dense and specifying 3 as the number of rows and 2 as the number of columns and an array of 6 elements. The first 3 elements, 1, 3 and 5, will fill the first column of the matrix, while the other 3 elements will be in the second column, as shown in res 0. Note here that we passed in an array of integers and it returned a matrix of doubles. MLlib uses the compressed sparse column format for sparse matrices. In this example, I'm creating a sparse matrix with 5 rows and 4 columns. In the sparse representation, I keep only the non-zero entries, so my array of values is going to be 34 and 55. I also need to specify which row each of the values is in. In this case, my values are in rows 1 and 3. The one remaining element we have to specify when creating a sparse matrix is this array of column pointers. This points each non-zero value to the column it belongs in. We will repeat pointer values whenever we have an empty column. If we look at the column pointer values for this sparse matrix, we have 4 values representing the pointers for each column, and the final value being the total number of non-zero values. Column pointers do not represent an exact physical location in the matrix. They simply provide visibility into which columns have non-zero values, and combined with row indices can provide physical location. The details of this data format have been designed to be efficient for column slicing and computing matrix vector products. These are common operations in data science. Here's a sparse matrix example. Here we see the code for creating the matrix we've just been looking at. Now that we've gone through local matrices, both dense and sparse, let's move our focus to distributed matrices. A distributed matrix is stored in one or more RDDs, distributed across Spark cluster nodes. Its row and column indices are of type long so as to allow big dimensionality, and the values are, as usual, doubles. There are 3 types of distributed matrices: a row matrix, indexed row matrix, and coordinate matrix. It is important to understand the differences between them in order to choose the most appropriate type for your particular problem. Even though the conversion between types is possible, this may require an expensive global shuffle across nodes. The first kind of matrix we're going through is called the row matrix. We use this kind of a matrix when our collection of vectors carries no meaningful row indices. So it may be when analysing anonymised data sets, such as no customer ID against a record. The row matrix is the most basic type of distributed matrix. It is a collection of vectors with no meaningful row indices. It is assumed that the number of columns is small enough to be stored in a local vector, since the row matrix is backed by an RDD of its rows and each row is a local vector. Therefore, a row matrix can be easily created from an RDD containing vectors. Here we look at a simple example of the creation of a row matrix. First, I create an RDD of vectors called rows by parallelizing 3 dense vectors with 2 elements in each. Now I create a new instance of row matrix named mat from the previous RDD. Since I had 3 vectors with 2 elements, I should get a matrix with dimensions 3 by 2. And indeed, numRows and numCols returns me exactly that. The indexed row matrix is quite similar to the row matrix. The difference between the two being that the former has meaningful row indices, which can be used for identifying rows and executing joins, while the latter does not. We use this kind of a matrix when the row indices are associated with some meaning or order, such as customer ID. Just like in a row matrix, the columns are stored in a local vector, but each row is now an indexed row, that is, a tuple containing a long-typed index and a local vector. So the indexed row matrix is backed by an RDD of indexed rows, and therefore can be created from an instance of the latter. It is also possible to convert an indexed row matrix to a basic row matrix by calling the method toRowMatrix, which will drop the indices. This is a simple example of the creation of an indexed row matrix. First, I create an RDD of indexed rows called rows by parallelizing 3 indexed rows, each one being a tuple of a long and a dense vector. Then I create a new instance of indexed row matrix named IDXmat from the previous RDD. The third type of distributed matrix is the coordinate matrix. It should only be used when both dimensions are huge and the matrix is very sparse. Unlike the other 2 types, there is no separate array for the values. The coordinate matrix is backed by an RDD of matrix entries, where each entry is a tuple containing the row index, the column index, and the value of the entry. Just like the previous types, the coordinate matrix is created from an instance of an RDD, in this case of matrix entries. But you cannot retrieve the original RDD since there isn't a rows attribute available. It is also possible to convert a coordinate matrix into an indexed row matrix with sparse rows by calling the method toIndexedRowMatrix. This is a simple example of the creation of a coordinate matrix. Just like in the previous examples, first I create an RDD of matrix entries called entries by parallelizing 3 matrix entries containing the coordinates for the values I want to insert in the coordinate matrix. In the example, I'm inserting the value 9 with the upper left corner of the matrix, followed by the value 8 in the second column of the second row, and then the value 6 in the second column of the third row. Then I create a new instance of the coordinate matrix, named coordmat, from the RDD I have just created. Having completed this lesson, we should now be able to understand local and distributed matrices, create dense and sparse matrices, and create different types of distributed matrices.